Afternoon, everybody. Today, I'm going to talk to you about how I feel the need for speed, and how I want to use particle accelerators to accelerate the development of fusion materials research. Before I begin, I'd just like to say it takes a whole team to run an accelerator lab, and in particular, I'd like to thank my advisor, Dennis, the accelerator team, Zach, Hartwig, Kessler, and my committee, Mike Short, Joe Minervini, and Graham Wright. So getting started, there's a couple prerequisites. I promise there's not going to be a lot about plasma physics. But first prerequisite is that fusion confinement uses magnetic fields. So a fusion plasma is really, really hot. And you can't use a material to contain it. But luckily, a plasma is also made up of charged particles. So what you can do is you can put it in a magnetic field, and the particles will spiral around the magnetic field lines. So some really clever scientists in the 1960s came up with a configuration called a tokamak. They took these field lines and they wrapped them around into a donut, as you can see here. And then they added a poloidal twist, so the short way around the donut, to make these field lines helical. So on the right, the cartoon of a magnet system can be used to create this configuration to confine a plasma. And I'm not going to go into the details. You basically, here's one of the magnet systems going around. They're all in different colors. But none of these magnet systems have permanent magnets. Permanent magnets are not strong enough to confine a fusion plasma. All of these systems, the toroidal field coils, the poloidal field coils, the central solenoid, all of them are electromagnets. You put a current through a wire and you make your magnetic field that way. And we think that new magnet technology could lead to a much smaller, faster integration cycle in fusion. So as part of my research, I participated in the ARC design study. And this actually started out as a class here at MIT. And what we wanted to do is apply this new magnet technology and see if we could design a smaller reactor. So up here, we have ITER. ITER is currently the largest fusion reactor being built in the world. I think it's actually the largest science project in the world at this point. And this is a scale comparison of ARC, which was the reactor that we designed. And so if you notice, both of them have the same power, and roughly the same power. And this is by design. This is a criteria of the class. So how are we able to generate the same plasma performance, the same fusion performance in a device this size as that size? Well, we were able to utilize this new magnet technology to get almost twice the magnetic field, 9.2 Tesla on axis, that ITER does. And so what this allowed us to do is shrink the volume of plasma by about a factor of 5. And so the whole device gets smaller as the plasma shrinks. And this is huge, because all of a sudden you have a 500 megawatt class device that you've moved from being a multinational government conglomerate to something that's probably cheap enough that a single utility could build one of these. Even more importantly, because ARC is smaller, we think that it could be constructed much faster than ITER. So the fusion community has built two devices that are the size of ARC. They're called JET and TFTR. And both of those devices were constructed on a timescale of about 5 years, whereas ITER is taking 20 years, maybe longer, to complete. So by applying this new superconducting technology, we think that we could rapidly speed up the fusion development cycle. So prerequisite number 2, I mentioned superconductors a couple times. So what is a superconductor? In short, it's a material that can carry current with no resistance in it. And in order to understand the rest of this talk, I need to explain something called a critical surface. So a lot of people know superconductors, you probably have seen something that gets really cold. So one of the things that defines a superconductor is temperature. But there's two other parameters. There's the magnetic field that the material is in, and there's also the current density inside of this material. And these three axes come together to form something called a critical surface. And underneath this surface, your material superconducts. But if you go outside of the surface, it just becomes a normal conductor, like copper, for example. And so this is some of the new technology that we're applying to ARC to shrink these reactor sizes. It's called high temperature superconductor. It's a little bit of a misnomer. High temperature in this case means about 90 Kelvin instead of 4 Kelvin, so both pretty cold. But still considerably higher temperature. This is what a tape looks like. And so Dennis made a comment about micron scale. So this whole thing, this whole tape is about 1/10 of a millimeter thick. And this little black piece right here is the actual superconducting material itself. All the rest of this stuff is buffer and silver overlayers and a copper overlayer for the tape that makes up the superconductor. But when this thing is cold, all of the current goes through this tiny micron-thick layer in the center. So why are these good? Well, one thing is that they can operate at high temperatures. You can also put more current through it. And they can also operate at higher magnetic fields. And this is important. Another really important thing about this technology is that it's commercially available now. It's not just something in the lab. I can actually pick up the phone or go online and call one of these manufacturers here and say, I'd like a spool of 500 meters worth of tape. And actually, we did this at MIT a few months ago in one of the labs that I work in. They bought half a kilometer worth of tape and built a 6 Tesla small demonstration coil with it. It's pretty impressive. For the visiting students, I think you're going to visit Alcator at some point, and you should check out the demonstration coil. It's pretty cool. So let's compare the technology that ITER uses head-to-head with the technology that ARC uses. So ITER uses these low-temperature superconductors called niobium-3 tin. And this is a slice out of that 3-dimensional critical surface plot. So here's current density on the y-axis, and here's field on the x-axis. And as you can see, niobium tin, as you increase your field, the amount of current that you can carry drops precipitously. This is a log scale, so it falls off a couple orders of magnitude as you go up from 12 to 24 Tesla. But HTS doesn't have this. So here's HTS in red. As you can see, even up to 24 Tesla, the current carrying capability of HTS barely degrades. And so this is what allows us to build these high field magnets that enabled the arc reactor to be built at such a small size. But there's a catch. So both low temperature and high temperature superconductors degrade under neutron bombardment. And the exact mechanism behind this is actually unknown, but we think it's related to defects inside of the tape itself. And this is a cartoon of what a typical low temperature radiation response looks like. You have on the y-axis the amount of neutrons that you put through, and then we'll call it tape performance on the y-axis. And so as you bombard the tape more and more, it actually generally improves performance a little bit, and then it drops off as you reach this critical fluence. We think this is related to something called flux pinning sites. What does this mean? Here's a little cartoon of a superconductor. We've got magnetic field lines that penetrate. So the high temperature type 2 superconductors can only exist if you have a certain amount of flux lines penetrating through the superconductor. But we also want to make a magnet out of this. So we're going to put current through it. And if you take an E&M, you can convince yourself in the right-hand rule, if you have a current going in that direction and a field going in this direction, you're going to have a force that pushes leftwards on the screen, a Lorentz force. So what counteracts this? You have an opposite force that comes from defects within the superconductor itself. And these defects exert what's called a pinning force, which keeps these magnetic field lines in place and keeps your superconductor superconducting. So talk a little bit more about this later. But it turns out that this damage to superconductors was the main limiting factor between making ARC even smaller than it was. This is a cutaway so this is a cross-section of the arc reactor, and this is the inside where the fusion core here in yellow is the closest to this D-shaped toroidal magnet right here. And this is a simulation that I ran with a Monte Carlo program to look at neutron transport. And one of the things that we did was try and shield these coils from the neutrons. So here you have your fusion plasma that's spitting out 10 to the 14 neutrons per centimeter squared per second. And by using a really good shielding material, we were able to cut it down by several orders of magnitude by the time it reached the coil. But there's this critical unknown. Turns out we actually don't know what the lifetime limit for HTS is. We do know what it is for low temperature superconductors because a lot of work has been done on this. But there's not a lot of data on the radiation limit to HTS. So we had to use kind of conservative limits based on the technology that exists already. And the reason for this is that neutron studies are difficult. You have to take your material and you have to dunk it in a reactor and you have to let it sit. It becomes activated. It's difficult to deal with. So there's really only one group in the world that's performed high fluence irradiations of the high temperature superconductor that we care about. And to make things even more complicated, the performance degradation changes based on the operating temperature of the tape, the applied magnetic field to the tape manufacturer, which basically translates to the chemistry that the particular manufacturer uses to make the tape, and possibly even the strain on the tape. And so that means that there's actually been no irradiations performed under the operating conditions for a compact high field reactor. Kind of guessing. So this is a big gap in the data. But this is where accelerators come in. So the title of the talk was about using accelerators to make things faster. And there's been a lot of work in fission trying to look at using ion damage to emulate neutron damage. In fission, you want to look at bulk material studies, and it takes a really long time to irradiate something. So what people have done is they've taken material samples. In this case, this is just an example from a study on stainless steel. They put the stainless steel in a fission reactor, irradiated it for a certain amount of time, I think up to roughly 1 dPa, displacement per atom. And then they took the same sample and irradiated it with 3.2 MeV protons. As you can see, the two curves are in pretty good agreement. The solid curve is the protons, the dotted curve is the neutrons. But there's really important fact, two really important facts. One of them is that if you notice, the temperatures between the two are different. Also, the energy is different. So fusion neutron spectrum, you get generally the highest energy you get is like 2 MeV for a neutron. But the protons were higher energy. So you were able, under different irradiation conditions, they were able to achieve the same types of damage. So the metric here was looking at these microstructural defects called loops. So it turns out that the irradiation conditions are very important. And of course, to date, no comparison studies have been performed on HTS tapes. This is where MIT comes in. So right now, you're here in the Status Center. And if you were to walk west and a little bit south, you'd get to Albany Street. And Albany Street, I think, is a pretty awesome place. I spend a lot of my time there. Probably too much time. But we have an amazing array of experimental capability. And just to name a few that are pertinent to my research, we have a 6 megawatt research fission reactor. We have an 8 Tesla fusion tokamak called Alcator CMOD. Right next to that, we have a high field magnet with the cryogenics laboratory. We have an accelerator materials test facility. There's a hot fib and SEM, which allow us to look at microstructural defects in irradiated samples. And there's a nuclear materials stress and corrosion lab. And these are just a few of the labs that exist all on the same street. This is like, I don't know, 1,000 feet from here to there. A lot of science crammed into a small space. So I spent a lot of my time working with accelerators, and recently have renovated a 1 megavolt particle accelerator called DANTE. DANTE is a 1 megavolt tandem electrostatic accelerator, has an ion source that can produce multiple species of different types of ions up to very high currents, but it can also run at low currents. And this is good because it allows us to test a wide range of irradiation conditions on tapes. And so this is an experiment I designed. This is a target assembly for irradiating HTS. Here's a beam collimator. It's kind of hard to see in this picture, but there's a little slit here. You take the beam from the accelerator and you impinge it on this surface, and a little bit of it goes into a slit. Then we have some electron suppression and a Faraday cup, which essentially allow us to collect the current that comes from the beam and impinges on the HTS. So it allows us to quantify how much we've irradiated things. So this is the front face of the sample right here. This is a short sample of HTS that I've obtained without the copper overlayer. And this is the whole thing mounted inside of the target assembly. So there's this target assembly here that this whole thing goes into. The beam comes from this side and goes through this beam tube, hits the collimator, and then impinges on the target and damages it using protons. And using some Monte Carlo simulations, I've shown that MeV light ion beams are actually pretty ideal for this type of irradiation. So one of the things that you don't want to happen is you don't want your entire beam to implant inside the tape. And so this is kind of blown up segment of the tape. So here's the silver overlayer. This is the 1 micron section of YBCO. And then this is the big Hastelloy buffer. And so 1 MeV proton beam goes right through the silver and the YBCO, which is the superconductor, and embeds itself in the Hastelloy. So you don't have to worry about hydrogen deposition inside the superconductor itself. In addition, the energy to the recoils inside the superconducting region is roughly constant. The absolute value doesn't matter very much because we can tune the energy of the accelerator to get whatever energy we want. But we do want the damage to be constant because neutron radiation is highly penetrating, and we want to emulate neutron damage as best as possible. And finally, a little bit about heating. So the damage rate on the accelerator actually turns out to be limited by heat. So if you take a beam with a current and an energy, you multiply those things, you get a power deposited on your target. And that power has to be exhausted somewhere. And because the target's in a vacuum, the heat removal is conduction limited. So this is a little simulation that I ran in ComSol to show our beam hitting on this target, and the heat goes out through this stock, out through the target assembly. And this is a pretty acceptable temperature rise, about 30 degrees for now. And this allows us to put about a microamp of current on target. And this is important. I'll get to that a little bit later. Oh, I also want to add, there's work underway to design an actively cooled target, so we can have an even finer control knob on the temperature, because like you saw a few slides earlier, the temperature is really important for this type of thing. While this is going on, I had some samples put in the research reactor, because it's just down the street, so why not? And these are going to be the control samples. Right here, this is a top view of the reactor. This is the reactor core. There's a tube that goes into the reactor that you can load samples in this little titanium rabbit. And this is actually the rabbit. This is from behind leaded glass. This is the rabbit with my samples in it. This actually illustrates one of the difficulties of using neutron irradiation, is that your samples become very irradiated. After 2 weeks, the contact dose to each of my centimeter-long samples was over 100 millirem per hour, which is pretty big. You can't like touch a sample like that. You have to remote handle it. It's pretty difficult to deal with those. So right now, I put a sample in, and I'm waiting for them to cool down and get less radioactive before I can work with them. But in the meantime, I use DANTE to irradiate some samples. So here's some data from this week, actually, of the first critical current measurements that I've made of proton irradiated samples. So how do you do a critical current measurement? Well, superconductor, like I said several slides ago, can conduct current with no resistance. So in theory, there shouldn't be any voltage drop across this conductor. So this is the experimental setup is you run a current through it and you take 2 voltage taps and you measure the voltage between the 2 of them. And as you increase current, there's a finite resistance because you have solder and the solder isn't superconducting, but it's basically flat here. And then all of a sudden at this point, you get a voltage spike. And this is the transition. So this is on that critical surface plot. This is where you go from superconducting on this side to normal on that side. And that occurs for the unirradiated tape at around 110 amps. Now, if you look at tape that I irradiated to about 4 times 10 to the 15 protons per centimeter squared, and you look at this curve, critical current transition happens far lower at about 30 amps. So we definitely degraded the superconductor using protons. And this is really exciting because I made some educated guesses about where to start, but it's great that on first try we were able to get a measurable degradation in the HTS. So now we're waiting on the reactor samples, and we're going to compare the two and compare the critical currents, and then if those are similar, actually take an SEM and look at the microstructure. So to conclude, we are the Department of Nuclear Science and Engineering, so I'll talk about the science and engineering contributions of this work. As far as science, this work will hopefully add sort of another dimension to this critical surface. It'll have the current density as a function of neutron fluence. So you take this, and then you bombard it with neutrons, and this critical current will drop by some amount. And so scientifically, this work will give us insight into the physical mechanism behind high-temperature superconductivity. And from an engineering standpoint, we'll be able to qualify new materials to be used in the design of fusion reactors. So knowledge of HTS damage limits will allow us to design the next machine, hopefully maybe even smaller than ARC, once we know more about the operating limits of this material. And all of this is made possible because of this huge array of experimental capability that we have all here at MIT. So I hope that leveraging these resources, this research will be able to contribute to the acceleration of fusion development as a power source for the future. Thank you very much.
Thank you.
Any questions?
You saw one other link, heat transfer is in almost in every application that we use.
Can you explain why, when you first start the neutron bombardment, the tape performance goes up slightly? What's the physical effect?
So the physical effect there is that, if we go back to here, so when you put a current through, you have this Lorentz force, and then you have this counter force made by defects. And so the current theory is that when you first start the neutron irradiation, you're actually creating more defects that actually help you for a while before they start to degrade the superconductor. So actually, there's manufacturers that are looking into possibly making higher performance tapes that won't be in a nuclear environment afterwards. They irradiate them for a little bit beforehand so they can get this little performance boost.
Any other questions?
Okay.
Thank you, Brandon.
Thank you very much.